It is possible that not having a separate neutral for the strobe light could cause it to stay on. In a multi-wire circuit, there can be capacitive coupling between the different circuits. This means that the voltage and current on one circuit can induce a small amount of voltage and current on the other circuits. If the neutral wire is shared between multiple circuits, this capacitive coupling can create a path for current to flow into the strobe circuit even when the relay is turned off. This could cause the relay to remain closed and the strobe light to stay on. When the relay turns off, the inductive load of the strobe light can generate a voltage spike. This spike can be transmitted through the shared neutral wire and interfere with the other circuits. This could cause the relay to remain closed and the strobe light to stay on indefinitely. To resolve this issue, it is recommended to provide a separate neutral wire for the strobe light. This will eliminate any capacitive coupling or inductive kickback from affecting the other circuits and ensure the proper operation of the strobe light. Firstly, check the wiring connections to make sure they are secure and correct. Secondly, test the strobe light on a dedicated circuit to ensure that it operates properly. Thirdly, contact a qualified electrician to inspect the electrical system and make any necessary repairs or modifications. Let's delve deeper into the concepts of capacitive coupling and inductive kickback to understand why a shared neutral can cause problems with sensitive electronic devices like strobe lights. Capacitive coupling occurs when two or more conductors are in close proximity. They act like a capacitor, storing electrical energy. In a multi-wire branch circuit, the ungrounded conductor's hot wires and the neutral conductor run parallel to each other. The alternating current in the ungrounded conductors can induce a voltage on the neutral conductor and adjacent circuits through this capacitive effect. Even though the neutral conductor is supposed to be at or near 0 volts, this induced voltage can create a small current flow. If the strobe light circuit is sensitive to voltage fluctuations or stray currents, this capacitively coupled current can be enough to keep the relay energized, preventing the light from turning off. The magnitude of capacitive coupling depends on factors such as the distance between the conductors, the length of the parallel run, and the frequency of the current. Higher frequencies and longer parallel runs lead to increased capacitive coupling. Now let's examine inductive kickback, also known as back electromotive force or back EMF. When an inductive load, such as the strobe light's transformer or ballast, is switched off, the magnetic field around the inductor collapses rapidly. This collapsing magnetic field induces a voltage in the inductor itself, opposing the change in current. This induced voltage can be significantly higher than the supply voltage, potentially reaching hundreds or even thousands of volts in some cases. The voltage spike is often referred to as inductive kickback. In a multi-wire branch circuit with a shared neutral, this inductive kickback voltage can travel along the neutral conductor and affect other devices connected to the same neutral. Sensitive electronic equipment, like the strobe light, may misinterpret this voltage spike as a continuous signal, causing the relay to remain closed and the light to stay on. The severity of inductive kickback depends on the inductance of the load, the speed of the switching action, and the presence of any suppression devices. Devices like diodes or metal oxide varistors, MOS, are often used to absorb or suppress inductive kickback voltage spikes. Here's a step-by-step breakdown of how to troubleshoot and resolve the issue of a strobe light staying on in a multi-wire circuit. 1. Verify the wiring configuration. Ensure that the multi-wire branch circuit is correctly wired according to the National Electrical Code, NEC, or applicable local codes. Check that the neutral conductor is properly connected to the panel board and at each receptacle or device. Look for any loose connections, damaged insulation, or other wiring defects that could contribute to the problem. 2. Isolate the strobe light circuit. Disconnect the strobe light from the multi-wire branch circuit and connect it to a dedicated 120-volt circuit with its own neutral conductor. This will eliminate any potential interference from other devices or capacitive coupling/inductive kickback effects. If the strobe light operates correctly on the dedicated circuit, it confirms that the issue is related to the multi-wire circuit configuration. 3. Check the neutral to ground voltage. Use a multimeter to measure the voltage between the neutral conductor and the equipment grounding conductor at the strobe light location. Ideally, This voltage should be close to 0 volts. A significant voltage reading indicates a potential problem with the neutral conductor, such as a loose connection, excessive current flow, or an imbalance in the multi-wire branch circuit. 4. Inspect the neutral conductor connections. Carefully examine all neutral conductor connections in the multi-wire branch circuit, including those at the panel board, receptacles, and any junction boxes. Look for any signs of corrosion, looseness, or damage. Tighten any loose connections and replace any damaged wiring components. 5. Provide a dedicated neutral conductor. The most effective solution is to provide a dedicated neutral conductor for the strobe light circuit. This eliminates any potential for capacitive coupling or inductive kickback from other devices in the multi-wire branch circuit. Run a new neutral conductor from the panel board to the strobe light location, ensuring that it is properly sized for the circuit load. 6. Install a surge suppressor or filter. Consider installing a surge suppressor or noise filter at the strobe light location to protect it from voltage spikes and electrical noise. These devices can help to mitigate the effects of inductive kickback and other transient disturbances. 7. Verify the strobe light specifications. Check the manufacturer's specifications for the strobe light to ensure that it is compatible with the voltage and current characteristics of the circuit. Some strobe lights may be more sensitive to voltage fluctuations or electrical noise than others. 8. Consult with a qualified electrician. If you are unable to resolve the issue on your own, or if you are not comfortable working with electrical wiring, consult with a qualified electrician. They can perform a thorough inspection of the electrical system and identify any underlying problems. Now, let's consider some additional factors that could contribute to the strobe light issue. 1. Harmonic currents. Nonlinear loads such as computers, electronic ballasts, and variable frequency drives can generate harmonic currents that flow in the neutral conductor of a multi-wire branch circuit. These harmonic currents can cause the neutral conductor to overheat and can also interfere with the operation of sensitive electronic equipment. 2. Unbalanced loads. In a multi-wire branch circuit, it is important to distribute the loads evenly across the different ungrounded conductors. If one ungrounded conductor is heavily loaded while the others are lightly loaded, it can create an imbalance in the neutral current, leading to voltage drops and potential problems. 3. Ground loops. A ground loop occurs when there are multiple paths to ground in an electrical system. This can create unwanted currents that flow through the grounding conductors and can interfere with the operation of sensitive electronic equipment. 4. Electromagnetic interference (EMI). External sources of electromagnetic interference, such as radio transmitters or industrial equipment, can also affect the operation of the strobe light. Consider shielding the strobe light or relocating it to a less noisy environment. In summary, the issue of a strobe light staying on in a multi-wire circuit can be caused by a combination of factors, including capacitive coupling, inductive kickback, harmonic currents, unbalanced loads, ground loops, and electromagnetic interference. By following a systematic troubleshooting approach and considering these additional factors, you can identify the root cause of the problem and implement appropriate solutions. Remember to always prioritize safety when working with electricity. If you are not comfortable working with electrical wiring, consult with a qualified electrician. They can ensure that the electrical system is safe and operating properly. Furthermore, it is important to comply with all applicable electrical codes and regulations when installing or modifying electrical wiring. The National Electrical Code (NEC) provides comprehensive guidelines for safe and effective electrical installations. Familiarize yourself with the NEC requirements for multi-wire branch circuits, neutral conductors, and grounding systems. This will help you to avoid common wiring errors and ensure that the electrical system is safe and reliable. Let's discuss some specific NEC requirements that are relevant to multi-wire branch circuits. NEC Section 210.4 covers multi-wire branch circuits. It defines a multi-wire branch circuit as a circuit consisting of two or more ungrounded conductors having a voltage between them, and a grounded conductor having equal voltage between it and each ungrounded conductor of the circuit, and which is connected to the neutral or grounded conductor of the system. NEC Section 210.4 requires the multi-wire branch circuit supply only line to neutral connected loads. This means that all devices connected to the circuit must be connected between an ungrounded conductor and the neutral conductor. Line-to-line connected loads, such as 240 volts appliances, are not permitted on multi-wire branch circuits. NEC Section 210.4b requires that multi-wire branch circuits have a means to simultaneously disconnect all ungrounded conductors at the panel board. This can be accomplished using a multi-pole circuit breaker or a combination of single-pole circuit breakers with a handle tie. NEC Section 300.13b requires that the continuity of the neutral conductor not be dependent on device terminals. This means that the neutral conductor must be continuous throughout the circuit, even if a device is removed or disconnected. This requirement is intended to prevent open neutral conditions, which can create dangerous voltage imbalances. NEC Section 408.3 requires that each neutral conductor be connected to a terminal that is identified for use with that conductor. This helps to prevent accidental connections between neutral conductors and other conductors. In addition to these NEC requirements, it is also important to follow good wiring practices when installing multi-wire branch circuits. Firstly, use properly sized conductors for the circuit load. The conductor size must be sufficient to carry the maximum current that the circuit is expected to draw. Secondly, use properly rated overcurrent protection devices, such as circuit breakers or fuses. The overcurrent protection device must be sized to protect the conductors from overload and short-circuit conditions. Thirdly, make sure that all connections are tight and secure. Loose connections can create resistance and heat, which can lead to fires. Fourthly, label the multi-wire branch circuit clearly at the panel board. This will help to identify the circuit and prevent accidental disconnections. Fifthly, test the multi-wire branch circuit after installation to ensure that it is working properly. Use a multimeter to measure the voltage between each ungrounded conductor and the neutral conductor. The voltage should be approximately equal between each ungrounded conductor and the neutral conductor. Also, measure the current flowing in each ungrounded conductor. The current should be evenly distributed across the different ungrounded conductors. By following these NEC requirements and good wiring practices, you can ensure that multi-wire branch circuits are safe and reliable. This will help to prevent problems such as strobe lights staying on, as well as other electrical issues. Finally, consider the age and condition of the electrical system. Older electrical systems may have deteriorated wiring, loose connections, and outdated components. If the electrical system is old or in poor condition, it may be necessary to upgrade it to meet current safety standards. This could involve replacing the wiring, upgrading the panel board, and installing new overcurrent protection devices. A qualified electrician can assess the condition of the electrical system and recommend appropriate upgrades. These upgrades should be made not just for a single strobe light problem, but so it will be safe overall.